Jai Hind, friends. Myself, Dr. Pankaj Goel, working as an assistant professor in EC department in AKGEC Garg Engineering College. Today, we will discuss a very important topic of optical lithography. Now, lithography is a process of transferring geometrical patterns from a mask to the silicon wafer. The regions where dopants have to be incorporated are selected. Those regions are selected where dopants have to be incorporated, and these regions are marked by a process called lithography. Lithography is sometimes also referred to as a photolithography because we use radiations in this process. In lithography, we have a mask in which the geometrical patterns are already present, and we transfer these geometrical patterns from the mask to the wafer. Little bit about the history of from where the word came into existence, why we are using the word lithography in VLSI. The technique was first used in 18th century, and the concept of transferring the pattern was used on a stone plate on which the pattern was engraved. So we put some ink or something on that engraved pattern and then press it down onto the paper or wherever we want to transfer the pattern. So the ink stained portions will leave its mark on the material. So that was the first concept of lithography. Now, the photolithography is about light silicon wafer printing, and the components that are required in a photolithography are mask, photoresist, and a ultraviolet exposure system. Ultraviolet exposure system is used to produce ultraviolet radiations. The type of lithography, depending on the kind of radiations we are using, radiation system we are using, we have three types of lithography. First one is optical lithography, in which ultraviolet radiations are used. Second one is electron beam lithography, in which instead of ultraviolet radiations we use electron beam. And the third one is X-ray lithography, where X-rays are used as a radiations. So optical lithography, as the name suggests, we are using ultraviolet radiations in this lithography process to give the impressions or patterns on the wafer. First of all, in this process, we start with coating the silicon wafer with a radiation sensitive polymer film called the resist or the photoresist. We can see here, this is one of the component here, photoresist. So first of all, we do the coating of the silicon wafer using a material which is radiation sensitive material, and this material is called the resist or the photoresist. Resist is a radiation sensitive polymer, that is, when it is exposed to a particular type of radiations, its properties changes. And this polymer is generally available in a viscous liquid form. Now, as this material is available in a viscous liquid form, the few drops of this resist are taken in a syringe and put 1 or 2 drops on the wafer, and then this wafer is spin at a very high speed to make a uniform layer of the resist on the top of the silicon wafer. We spin the wafer so that we have a uniform layer of resist on the top of it. And by varying the spinner speed, we can adjust the thickness of the layer. Now, once we have applied the photoresist material on the surface of silicon wafer, the next step is that we have to expose this resist using ultraviolet radiations. Now, here we can see in this figure, this is our silicon wafer. This is our silicon wafer, and this is another layer that we apply before we do the lithography process. That is a silicon dioxide layer, which is a insulating layer or dielectric material. Which is a dielectric material, and on the top of this layer we apply the photoresist. This is your photoresist. With the help of a injection and spinning the wafer, it is uniformly deposited on the top of the wafer layer. And then there is a mask. This is our mask. Mask is having some areas through which radiations can pass, and there are some areas where radiations cannot pass. So, there are some parts of the mask which are opaque, and some parts are transparent. So, through the transparent areas, radiations can pass through the mask, and when in those areas where the mask is opaque, the radiations cannot pass. Okay. So, a mask plate is nothing but a glass plate with the transparent and opaque regions. So, only those regions of the mask which are transparent to the radiation allow the radiation to fall on the semiconductor, and because our resist is radiation sensitive, so the properties of the resist are going to change when the resist is exposed to radiations. So, in some cases the exposed region might get softened, and in some other cases the exposed region might get hardened. In those resists in which the exposed areas get softened, they are known as positive photoresist, and in those resists which when exposed to radiation get hardened are known as negative photoresist. So, there are two types of photoresist that we have: positive photoresist and negative photoresist. In positive photoresist, what happens is the exposed areas get softened, and in negative photoresist the exposed areas get hardened. Now, what is the consequence of changing the properties of the photoresist? Means when it gets softened, what happens, and when it gets hardened, then what happens? How it is useful? That is what we are going to discuss next. Now, after exposing the wafer to the radiation for a certain period of time, the wafer is soaked in a developer solution. We call it developing step. Okay. Now, here in this figure, please see, we have shown the pattern transformation on the photoresist. The positive photoresist directly underneath this is exposed to radiation, and now it becomes soft. Now it becomes soft and therefore it is easy to remove. Okay, so this is the case of positive photoresist, because the resist material gets soft in the areas where it gets exposed to radiations. It is easy to remove. The photoresist is easy to remove from those areas. Now, when we put the wafer in the developer solution, the exposed portion of the photoresist go away, leaving with resist films only in the unexposed regions, as shown in the figure below. Here we can see the photoresist only remains only in those areas where radiations were not falling on the photoresist. From those areas where radiations were falling and the resist become soft, they are removed by soaking the wafer into a developer solution. Now, after this, the next step is etching. We can see here the next step is etching. Etching step is nothing but removal of SiO2 layer from the exposed areas, because if SiO2 layer is not removed, dopants cannot be incorporated into the wafer. So, from those areas where we have removed the photoresist in the developing step, now in the next etching step, from those areas SiO2 layer is to be removed, and here we are using a diluted hydrofluoric acid solution. So, we can see here the SiO2 layer is removed from these areas. No SiO2 layer. Similarly, no SiO2 layer in this section. So, these areas are now ready for dopant incorporation. Okay. After the removal of silicon dioxide layer, the remaining photoresist are to be removed. After SiO2 layer is etched away from the exposed areas, the purpose of the photoresist is achieved, and now we have to remove the photoresist layer by the etching process. So, here we can see there is no photoresist, no photoresist. Now, we can compare the pattern on the mask with the pattern on the silicon dioxide layer. The opaque region in the mask correspond to that pattern of the oxide. And now, why we are doing this lithography process is for doping. Now the doping can be done in the regions corresponding to the transparent portions of the mask. As we know, this type of resist which gets softened when exposed to radiation is known as a positive photoresist. The pattern of the mask and the pattern on the semiconductor is identical. Here in this figure, we have shown all the steps of the lithography process. Like, first of all, we have to take a wafer, then on the wafer we have to apply a SiO2 layer, and after that we have to apply a photoresist layer. Then that wafer is exposed to radiation with the help of a mask and a ultraviolet radiation exposure system. If we are talking about positive photoresist, the exposed areas get soft, and those soft areas are to be removed with the help of a developer solution. This step is known as developing step. After that, we are using a etching step in which we have to remove the silicon dioxide layer from the exposed areas so that the doping can be done. And after SiO2 layer is removed, in the final step, we have to remove the remaining photoresist material from the wafer. So these are all of the steps in a optical lithography process. So let us discuss a bit about negative photoresist also. As we know, in negative photoresist, the areas which are exposed to radiations, they get hard. Okay, and in that case, they make a complement of the mask pattern etched on the semiconductor. Okay, and this kind of resist is known as negative resist. Next, here we can see there are examples of resist are given: positive photoresist and negative photoresist. Example of positive photoresist is MP 2400 and HPR 206, and example of negative photoresist is Kodak Microneg 747. Let us go into the further detail of what a photoresist material comprise of. A photoresist material has two components known as a resin and a photoactive compound. The photoactive compound is a dissolution inhibitor, and when this photoresist is exposed to radiation, then this photoactive compound is destroyed by the light. So the resin becomes more soluble in a aqueous developer solution. So we have two parts, a resin and a photoactive compound. Photoactive compound is when exposed to radiation, it gets destroyed and the resin become more soluble. The unexposed regions do not swell much. And here we obtain a higher resolution in case of positive photoresist. And positive photoresist are being developed for exposure at shorter wavelengths where higher resolution is possible, for as low as wavelength less than 250 nanometer. Okay, now let us see the chemical nature of a negative photoresist. In case of a negative photoresist, it also contains two parts, chemically inert polystyrene rubber, which is the film forming component, and a photoactive agent. Now, what happens when this negative photoresist is exposed to radiation, exposed to light? Then the rubber and the photoactive agent form the crosslinks. making rubber less soluble in an organic developer solvent. So, when after the exposure of the radiation, when this negative photoresist is soaked in a developer solution, the unexposed regions get removed, because after the exposure, the rubber make a cross link with the photoactive agent and therefore it becomes less soluble. So, the unexposed regions get removed when they are soaked in a solution. Okay. Here we can compare the output of a positive and a negative photoresist. See, when positive and a negative photoresist are exposed to radiation, in case of positive photoresist, the output pattern on the wafer is same as on the mask, whereas in case of a negative photoresist, the output pattern on the wafer is the negative of the mask, negative of the pattern on the mask. So, we can see here the radiations are allowed to pass through these regions. So, in case of positive photoresist, the resist become soft and therefore get removed from these areas, and from these areas the photoresist are etched away. Whereas in case of a negative photoresist, when it is exposed, then it become hard and therefore it is not etched away from the exposed areas. The resist is removed from unexposed area. This is your unexposed regions. Unexposed region, and this is your exposed region. So, photoresist is removed from the exposed regions in case of positive photoresist, and photoresist is removed from unexposed regions in case of negative photoresist. Okay. The next, the two main figure of merit in a lithographic process is resolution and the throughput. Okay. Resolution is the minimum feature size as well as the accuracy with which the minimum feature size can be transferred to the silicon wafer, and throughput means how many wafers can be processed in a given time. So, this actually tells about the cost of the production. So, if the throughput rate is less, the process is going to cost more. We have three types of masking: the contact printing, proximity printing, and the projection printing. The images, the figures of all the three types of printing is shown here in this figure. Here we can see this is our contact printing. Here in this case, the mask and the photoresist. This is our photoresist. Mask and photoresist, they are in contact. With mask. Whereas in proximity proximity printer, there is a gap. Okay, and in case of projection printing, we are using imaging optics system between the wafer and the mask. Now let us see the pros and cons of all the three type of printing systems. Contact printing, here the wafer is in contact with the mask. So because the wafer is in contact with the mask, the resolution is going to be very high here in this case, because wafer is in contact with the mask. So when the radiations are falling on the wafer through the mask, they don't get scattered. Okay, so they don't get deviated from their paths, because wafer and mask are in contact with each other, so they don't get a gap to get scattered. So the resolution is very high in case of contact printing, but it has its drawback also, and the drawback is the mask, because it is in contact with the wafer, it gets damaged. There is a drawback of contact printing, and the drawback is that because the wafer is in touch with the mask get defects when it is used again and again. For example, it has been found that after 15 exposures, we get 37 defect per square centimeter, and when we had after 5 exposure, we had on an average 13 defect per square centimeter. So because they are in touch with each other, the defects are developed, and we have to we cannot reuse the mask again and again. So it add to the cost of the system. And the defects include pinholes in the chromium film, scratches and star fractures. Now, to remove this drawback of contact printing, that our mask get damaged very frequently, instead of keeping the mask in contact with the wafer, we can maintain a certain gap. So that is the proximity printing, where there is a bit of gap between the mask and the wafer. But the drawback of this is that because there is a gap between the mask and the wafer, after passing through the mask, the radiations get deviated from their path, they get scattered, they get diffracted, and so the resolution is not that good as in case of contact printing. Here this is our mask and this is our wafer, and there is a gap between the two. This is our mask with the width W, and this alpha is the diffraction half angle. So for a certain value of a parameter Q, we get better resolution, and the Q is given by W under root of 2 lambda G. Larger the value of Q, the more faithful the image is. So here we can see we have a point source, and here we have an extended source. Extended source has been obtained with the help of a mirror here. So instead of a point source, if we use extended source, we get a lower value of alpha. The value of alpha is less. Alpha is divergence half angle, and if the value of alpha is less, it is good. So typically a few degrees only and it is optimized for the smallest feature to be obtained. So, instead of point source, if we use extended source, the value of alpha, the diffraction half angle will be less, and that is beneficial to obtain the smallest features on the wafer. And in the last, we have a projection printing. Projection printing give you the benefits of higher resolution and at the same time the greater mask life. In projection printing, we can see we are using some imaging optics in between the mask and the wafer. This is our mask, this is our wafer, and in between there is the imaging system. The resolution of an optical imaging system of numerical aperture sin alpha with light of wavelength lambda is according to Rayleigh's criteria, that is, it is 0.61 lambda upon sin alpha. So, that is the resolution of an optical imaging system of in case of projection printing. Secondly, the Rayleigh's depth of focus is given by plus minus lambda upon 2 sin square alpha. Further study on this topic, the book VLSI technology authored by SMZ may be referred. Thank you very much.